What is second law? The second law tells us that processes in nature have a direction. For example, heat flows from higher temperature to lower temperature, not the reverse. Water flows downhill, not uphill. Time moves forward and not backward. Even though the first law allows both direction, but the second law tells us only one direction is physically possible. This is because energy also has quality, and during any real process, the quality of energy naturally deteriorates. Thermal energy reservoir. Before we can fully understand how heat engine and refrigerator system operate, we first need to introduce the concept of a thermal energy reservoir. A thermal reservoir is essentially a large body, such as the ocean, a lake, a river, or even the atmosphere, that has extremely large thermal capacity. Because of this, it can absorb or supply a significant amount of heat without undergoing any noticeable change in temperature. In thermodynamics, we treat reservoir as ideal heat source or heat sink. A hot reservoir provides heat at a constant temperature, while a cold reservoir absorbs heat without affecting its own temperature. This concept is crucial because every heat engine must receive energy from a hot reservoir and then reject part of that energy to a cold reservoir in order to complete its cycle. Similar to refrigerator and heat pumps transfer heat from a low temperature reservoir to a high temperature one. By modeling this system using thermal reservoir, we can analyze real power plants, refrigeration cycle, and many engineering applications with greater accuracy and simplicity. A heat engine. Heat engine is a device designed to convert heat energy into mechanical work, and it operates continuously in a cyclic manner. For a heat engine to function, it must be connected to two thermal reservoirs, such as a high temperature reservoir that supplies heat and a low temperature reservoir that absorbs the waste heat. During each cycle, the engine receives a quantity of heat from the hot reservoir. Part of this heat is converted into useful mechanical work, and the remainder must be rejected to the cold reservoir. This rejected heat is essential because it allows the working fluid to return to its initial state and complete the cycle. The net work produced by the engine is simply the difference between the heat received and the heat rejected. The performance of a heat engine is measured using thermal efficiency, which is defined as the ratio of the useful work output to the heat input. However, according to the second law of thermodynamics, no heat engine, no matter how perfectly designed, can convert all the heat is received into work. Some portion of the heat must always be discharged to the low temperature sink. This means that the efficiency of any real or ideal heat engine will always be less than 100%, and this limitation is a fundamental consequence of the second law.
The Kelvin Planck statement of the second law describes a fundamental limitation of a heat engine. It states no heat engine can operate by receiving heat from a single thermal reservoir and converting all into the heat work. In other words, a heat engine cannot produce work as it only output. That means that achieving an efficiency of 100% is physically impossible. Heat rejection is not a design flaw or an engineering weakness. It is a fundamental requirement imposed by the second law. Even the most technologically advanced power plants, whether nuclear, solar, and fossil fuel, they must still reject large amount of waste heat into the lakes, river, tower, or atmosphere. This statement reminds us that second law set an absolute upper limit that no engineer or technology or a matter can bypass. It forms the backbone of how we evaluate the design and improve all power generate system. Next, we move to refrigerator and heat pump. This device operates in the opposite direction of heat engine. Instead of converting heat into work, this system uses external work to transfer heat from a lower temperature region to a higher temperature region. This means they reverse the natural direction of heat flow. This behavior is described by Clausius' statement of the second law, which tells us that heat cannot flow from a colder body to the hotter body without the input of work. This is why refrigerators must consume electricity. They are constantly work to remove heat from a cool interior and push it into the warmer room outside. The performance of this device is measured using the coefficient of performance or COP. For refrigerator, the COP defined as amount of heat removed from a cool space divided by work input. For heat pump, the COP measure how much heat is delivered to warm space per unit work supplied. In a simple term, your fridge is not producing cool air. It is actively doing work to move heat out from a food compartment. Without the continuing input of work, heat would naturally flow back in the refrigerator, and the refrigerator would stop cooling. The Carnot cycle is the most effective heat engine that can operate between two temperature limits, and its ideal cycle composed of 4 perfectly reversible processes. First, an isothermal expansion at higher temperature, where the system absorbs heat from the hot reservoir while performing work. Second, a reversible adiabatic expansion, in which system continues to expand without heat transfer and causing its temperature to drop. Third, an isothermal compression at lower temperature, where heat is rejected to the cool reservoir. And finally, a reversible adiabatic compression, which is bring the system back in the initial state. In conclusion, the second law of thermodynamics is one of the most powerful principles in engineering because it is explains the direction of natural process and the limitation of engineering conversion. It tells us that energy has quality, not quantity, and that heat engine can never reach 100% efficiency because some heat must always be rejected. And it also shows that refrigerator and heat pump require work to transfer heat from cool to hot region, and reversible process, although impossible in practice, provide the benchmark for maximum performance. And the second law determines what is possible and what is impossible in any thermodynamic system. It governs the behavior of engines, power plants, refrigerator and heat pump, and even chemical reaction. Ultimately, it shapes how every energy-based system in the world operates, and it is essential for designing efficient, reliable, sustainable engineering solutions.